Okay, now continuing with what we were discussing the last time, we were I told you about the basics of data structures, rather the basic definition of data structure, which refers to the logical or mathematical placement of items or organization of items. And by organization we mean that they are actually placed inside the memory of a computer. And when we say memory, we refer to both the secondary storage devices as well as the RAM, right? Again, we know that the RAM has limited capacity. Usually it's 1 GB, 2 GB, 3 GB, or something maybe 10, 9 GB, but it's not as large as the hard disk or the secondary storage device is, which is usually in terabytes these days, or maybe 250 or 600 GBs, and it has multiple disks. So the organization of the data by the data structure refers to both. It refers to its organization in RAM, and it also refers to its organization in the secondary storage device as well. Of course, we know that the fabrication technology of RAM is such that it's a sort of electronic device. So whenever we want to access something from RAM, or we want to retrieve something from RAM, it just takes a fraction of a second, whereas the hard drive uh, basically has a mechanical structure, right? So of course, if you save something in a 1D array in the RAM, for example, this is a 1D array, and the same 1D array, okay, let me change the color, it's the same 1D array if it is stored in the secondary storage device, right? So both of them will have same organization of the data, but here it will be very quick, because it's the fabrication technology of the RAM is such that it's quick. And the secondary storage device, although it will consume the same amount of memory as it would have consumed in the RAM, but when we retrieve the data, it involves a lot of mechanical movement. For example, if you let me try to visualize uh, a fragment of a hard disk. So it's a disk with its I think it's from like this place, it's with its read write head here, right? So that if it wants to read something from a particular sector on the disk has to be rotated, and then this read write head has to be placed on the proper location from where the data will be retrieved. So all this, although the data structure in which the data will be stored may be very quick, may be very efficient, but if it is placed on an inappropriate storage device, its performance will be slowed down. But again, in this particular course, we will be dealing with all sorts of data structures, which will not only be able to be saved in the RAM, but they can also be saved in the secondary storage device, right? So this is slow, but again this is limited. So at times we may need some data structure to be intentionally placed into the secondary storage device, because of the limitations of size which we have in the RAM, right? So this these are some data structure which we already I introduced to you in the last lecture, and I think we were here. Now this is yet another data structure which is called stack. Now stack, although I am just giving an introduction of the data structure, we will be creating and evaluating different functions of the stack, and we will be doing performance analysis of different functions of stacks when we come to the details of this particular uh, topic. But for the sake of introduction, a stack is a data structure which has only one end. Now if you want to place something into the stack, you will have to use this end, and if you want to take something out of this stack, you will only have to use this end. So the only thing, for example, if you see, this is basically a linear array with its index 0, 1. I could have started from here, but it totally depends upon your implementation. So let's assume our index 0 is this is index 1, this is index 2, this is index 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. Now this stack has total 13 slots starting from 0 to 12, right? Now whatever we have to place into this stack, we will be inserting it in slot number 12, and then if there are free slots, it will be moving down. And if you want to access some particular item in the stack, the limitation here is that you can only see the index number 12, right? You cannot see indices below this particular index, right? If you want to retrieve something which is, let's say, at index number 5, you will have to make sure that all of the items from index number 6 to 12 are retrieved. They are retrieved, and then this index, the value at the index number 5 will move here, and then you will be able to retrieve it, right? So this is the rule of the stack. Now there are a lot of applications of the stacks which we will be covering most probably in a couple of weeks. One of the application of the stack is the way we solve a particular mathematical equation. Now we for example 1 plus 3, okay, 1 plus 3 multiply by 7 divided by 8, right? So we'll be writing particular algorithms which will be actually using stack to solve such and other mathematical equations, right? Then we have another data structure which is queue, and if you see the stack and queue, there is one obvious difference, that in queue there are two ends, right? The first end is the in, or we call it the front of the queue, and the other is called the out, or we call it the exit or back of the queue, right? So all the items, if you want to place an item into the queue, we will be storing it here, and if you want to retrieve an item from the queue, we cannot do it from here. We will be retrieving an item from this particular location of the queue. Again, we can give it indices 0, 1, 2, and this totally depends upon the implementation which you have done for the stacks and for the queue for that matter. For example, if you see here, this queue is apparently maintained in an array. That is why I have put indices here as well. But we could have, we can implement a queue which is actually stored in a linked list, right? So, and if we make a queue which is stored in a linked list, of course, then we will not be putting indices here. Now, so this is how it works, and in real life, it's the queue is simple. For example, if we have a bank and there is a person sitting here, he is accepting, let's say, electricity bills. So the first person who comes here, he will be in front of the queue. The next person who has to arrive, he is not going to come here. He will be using the next slot, and then the next person, he is a bit smaller, okay. Now, and the next person, so they are basically making a queue. Commonly we call it a line, but queue is the proper word. So they are making queues. So if a new entry has to come, the new entry will be here. But if somebody has to exit from the queue, he or she will be exiting from this place of the queue, right? So the queue is a data structure which has two ends, in and out, whereas a stack is a data structure which has only one end, which is used for both for in and out as well, right? Now again, what is the need of data structure, right? For example, if we only knew an array, So apparently we can store a lot of things, maybe everything in this particular data structure and array. So what is the need to have data structures, and why to go with all the hassle of learning and implementing all possible sort of data structures, right? So the basic uh, methodology use data structures is to basically organize your data set so that it can be retrieved, it can be facilitate efficiency in terms of storage of the data first, then retrieval of the data, and then manipulation of the data. These three items are very important for every data which is to be stored, right? So for example, if a new student gets admitted, so we need to have his or her record in some particular file and in some particular data structure. And then maybe later in the second semester, or maybe not next second week, we may need to have to retrieve that data to maybe assign some hostel room number, maybe assign some courses in the CMS and so on and so forth. And then maybe we need to manipulate the data as well, maybe to compute whether or not the student has achieved the highest GPA, or maybe the student has gone on probation. So we will have to retrieve the data and manipulate the data, but for that we will have to store the data. So all this requires data structures. Again, we can do all this using a 1D array, only one data structure, but we need to do it in an efficient manner, right? And by efficiency, later on when I'll be talking about the analysis of algorithms and analyzing your code, there we will come to know that just writing simple piece of code is not enough. We have to make sure that we write efficient codes, right? And then as a computer scientist, we need to know the skills through which we can measure how efficient, and measure and quantify that how efficient a particular piece of code is. For example, now see if he for okay, let me rub it. For example, there are two persons, right? Okay, now there is another person. Okay, this now if I want to, and both of them are students, right? This is student 1 and this is student 2, and I want to know which one of both of these is much, or rather is a better student. How can I say, or how can I judge that this particular student is better and the other one is maybe a weaker one? Maybe this guy is tall, maybe based on that, but again I want to know who is the better student, right? So if I mark here, for example, this student has a CGPA of 3 point, let's say 6, and this student has, I know you must be thinking to assign him 2.7, but I am giving him 3.9, right? So obviously based upon this quantitative value which represents CGPA, we can clearly see that this particular student is a better student, or we can say efficient student, right? So similarly in programming, we will have two files, or two algorithms, or two pieces of codes, and our task as a computer scientist will be to gauge, to measure these two files, so that we can tell that which one of these two files is more, or these two piece of codes is better or is efficient. So this we will be doing in the most probably in the next lecture, where we will be analyzing various pieces of codes and we will be gauging their efficiency, right? And there are mechanisms for that. Broadly speaking, the technique or the domain is known as asymptotic analysis. Will be or complexity analysis of a piece of code, and of a particular data structure. So don't get afraid from the terminologies, because when we will be explaining that these technologies, most probably you are going to grasp these terms and the concepts, inshallah. So the need of data structure is to have efficient storage of the data, efficient retrieval of the data, and manipulation of the data, which should be efficient. The focus here is on efficient, right? To give you an example of efficiency, for example, if you purchase a new mobile phone, most probably it's like this, and there you have another mobile phone, maybe it's like this, and every mobile phone has this screen unlock facility where you have to swipe your finger from, let's say, from here to here, or maybe you can have some pattern to swipe and unlock your screen. And just assume that if you swipe this, you get this new phone, and you swipe your finger across it, and it takes, let's say, 3 okay, 3 is enough, 3 seconds to get unlocked, right? So apparently this 3 seconds is small, but if you okay, let us do it. I swipe it, 1 2 3. Now it is a huge amount of time which is it is taking to get unlocked, right? Versus if for example this is another mobile phone which takes, let's say, 0.25 seconds, for example, to get unlocked, right? So 0.25 as compared to 3 seconds is far better. So both of them may have written correct code to make sure that when a finger is swiped on the screen, it gets unlocked and you see the menu. But again, this phone is far better in terms of efficiency. So here in this particular course, the focus is always on achieving efficiency, and efficiency can only be achieved by optimizing your code, and optimization can only be achieved when you have variety of options to store your data structures and a variety of options in terms of algorithms which you can write to retrieve your the information stored in the algorithms, right? So the design issue, select and design appropriate data types. This is the real essence of the object-oriented programming. And remember, if you recall the course of object-oriented programming, we covered C++ in that particular course. But again, you can use object-oriented programming, or you can do object-oriented programming in Java, and then there are other languages as well which provide object-oriented facility. And this brings to my mind another topic that we will be, when we do some coding in this particular course, we will again be using C++ because of the background which we have. We can switch to Java as well, but again we will be covering C++. But you may find books and topics and lectures which cover data structure using C only, right? And maybe Python, or maybe, let's say, there was in old good days there was a language named Fortran or Pascal, which is presently used as well depending upon the domain. So different data structures can be created and developed in multiple languages, right? But again, our focus, our implementation will be on C++, right? But if you want to use another language, I have no issue with that, right? Now, this is important because the basic focus of the data structure is to optimize a couple of operations which we can perform on, or which we will be performing on data structure. And the key operations which are very important are these 4 operations, right? For example, you have a system in which you have stored the name of a person, maybe his or her address, right, and maybe age, and again cell number. Now these are enough, right? Now There are a whole lot of operations which can be performed on this set of data, right? There are a whole lot of operations. For example, I want to find the number of A's which are there in the name of a person. For example, if a person name is Zahid, so there is only one A here, right? So this is an operation which can be performed on this data, right? Perfectly fine. I can come up with another operation, for example, which says that if the age of this person is greater than let's say 30 or not. This is another operation which can be performed on the data, right? But again, there are some operations which are performed on almost every data, almost, not always, but they are performed almost on every data. These include the insertion of a record. For example, this is such is the structure of a record which is placed, let's say, in the let's assume the NADRA, National Databases and Registration Authority. When we go to make our NICs, for example, they store this information. So insertion is the operation which is almost always performed on any data. Then deletion is another operation which is almost always performed on any data. For example, you've entered a record. For example, you've entered a record of a patient that he or she has been admitted in a particular ward on stuff, and then the patient gets well. Then you may delete that particular record, right? So that deletion may occur. I gave you an example of hospital. This can be any example. Updation, for example, the student record management system. In the first semester, the student scored 3.9 GPA. And the second semester, the student scored again 3.8 GPA. Now, his or her CGPA needs to be updated, right? So, insertion, deletion, updation, and searching. These are the 4 key operations which are performed on almost all type of data, right? So, and these 4 operations are actually called the dictionary operations, right? These 4 operations are known as dictionary operations, right? So the purpose of the data structure generally is to make sure that the proposed data structure, whether it be a linked list, right? Whether it be a linked list, whether it be an array, whether it be a, let's say, a stack, right? Stack, whether it be a queue, it performs well on these 4 operations. Generally speaking, we call these dictionary operations, right? So these are very important for operations. You create new data structure, maybe tree, you create a new data structure, you have created a tree and you want to analyze how efficient it is. So do evaluate its performance on insertion, deletion, updation and searching operation, the dictionary operations, right? Again, remember, I have not explained to you how can we do the evaluation, right? The evaluation or evaluating a particular data structure or a particular algorithm, piece of code is a different topic which we will be covering inshallah in next lecture. But again, the basic purpose of data structures and algorithm is to make sure that these dictionary operations perform well on the data structure. Again, there are other operations like sorting and merging, but these operations are not among the dictionary operations because they are not very commonly used on various data, right? So that's it for the introduction. I think we are done with the introduction, and inshallah in the next lecture we will be covering the analysis part of the algorithm, which is very important in this particular course as well, and it will be important for your future courses as well, inshallah.